introduction. Thanks very much for having me here. I'm deeply honored. So I'm Nung-Kun Yu. So the title of my talk is Towards Efficient Reasoning of Quantum Programs. So let me first start with some quantum computation milestones. So in the early 1980s, the two scientific giants, Richard Feynman and Yuri Manin, they come up with the idea that of quantum computation. So why do they want to introduce this? Because that when they are doing computation, or when they want to simulate the evolution of a quantum system, they find that do it with a classical computer, with a computer at that time, is very costly because quantum systems with 100 bits or quantum bits has parameters like 2 to the 100 complex numbers. So the idea is like, okay, why don't we just so the running it on a classical computer requires exponential time and the space. So the idea is like, why don't we just their idea is like, why don't we just regard the small quantum systems themselves as a quantum computer, and afterwards, then we just get a result. So in 1984, so Brassard and Bennett come up with, they show that, okay, quantum computer, the idea can really help for secure communication, in the sense that with a quantum communication, they can provably securely establish shared random bits between two parties. So this is called BB84, the Brassard and Bennett at 1984. And the big news in the 1990s is like Peter Shaw showing that with a quantum computer, one can actually factor a large number in polynomial time, I mean. So until now, the best classical algorithm requires like a quasi-polynomial or way more time than this polynomial time. So it's not known yet whether factoring is feasible in polynomial time with a classical computer. This is a very big question. But with quantum computer, you can do that. And in 2008, that HHL algorithm, so the research group at MIT, they show that, okay, one can actually solve a linear equations, AX equals to B, linear systems within polylog time, given where conditional number of the matrix A. And we know that this is impossible with a classical computer, because in classical computer, if we want to solve the linear systems, we need a polynomial time. And in recent like 3 years, like Scott Arison and comes up with the quantum supremacy, and two proposals of quantum supremacy, and using the two proposals were implemented by Google as a Nature paper called Quantum Supremacy, and also another paper by USTC in China called boson sampling. So they both show that under some complexity assumption that a quantum computer can do much better than classical, and they implemented the quantum protocol. So the quantum programming language research is the process of assembling sequence of instructions, and that can run on a quantum computer. So why do we need that? So we want to build a quantum software system, and also we want to verify quantum algorithm and implementations. And there are many other applications as programming language applications in classical computing. And there are many languages was developed to express quantum algorithms using the very high-level constructs. So for instance, Microsoft's Q#, and IBM's Cirq, and Google's Qiskit. Sorry, make a mistake. So it should be IBM's Qiskit and Google's Cirq. So let's look at the classical program. Classical programs usually like for transformational classical programs. With input bits, the output is bits. And for quantum program, usually we take quantum bits as input and get quantum bits as output. And then we perform quantum measurement to extract classical information. So the outline of this talk will be 4 parts. So the first is the basics in quantum computing. So this is the quantum bits, or in short, we call it qubits. So the description usually we can regard it as a 2-dimensional vector. We use the CAD-BRA notation, which is usually called Dirac notation. So psi is A0 CAD0 plus A1 CAD1. So in vector version, it's like A0 A1. And it's normalized, means that the 2 norm is 1. And the gate or the unit, or usually is a unitary, which transfer a quantum state to quantum state. And the application of the gate on the state is just a matrix multiplication. So suppose the initial state is psi, then we apply the gate U, then we get the output U psi. So U is a matrix because it's transfer vector to vector. So for instance, we can have a two-dimensional unitary, which is U00, U01, U10, U11. So you can use the diagram to see that it just maps 0 to 0 with amplitude U00, and maps 0 to 1 with amplitude U01, map 1 to 0 with amplitude U10, and maps 1 to 1 with amplitude U11. And you can verify as long as it's unitary, it preserves the 2 norm. And for quantum measurement, it's like this is the only way that we can extract classical information from the quantum system. So we all heard about Schrödinger's cat for the caton over there. So the idea of the mathematical description is like given the psi as what we described as A0 CAD0 plus A1 CAD1. So we apply quantum measurement, which we denote as M1, M0, and M1. So then if the outcome is M0, then the state collapses to 0. And we can see this event happens with probability A0 squared. And if we get result M1, then we get with probability A1 squared. So this is for giving you more intuitions of what is quantum gates, it's like, let's first look at the classical gates. So we have NAND gate and NOR gate, right? So we can have 2 income and 1 outcome. For quantum, it's slightly different because we usually ask the input and output with same dimension. So for X gate, which is called a polygate, and H gate and CNOT gate. So you can see the X gate is the matrix version of X gate is just a flip, maps 0 to 1, 1 to 0. And H gate is which is usually called Hadamard gate. So and the CNOT gate is more intuitive. So suppose we input with 2 bits A, B. So CNOT is called control NOT. So the first bit is control. The second bit is flip. Is not. So as long as A is 0, then B does not change. But if A is 1, then B flip. But one should regard this as a matrix version, so or the linearization of this version. So you can write the matrix version of CNOT as 1, 1 with a NOT. And for H gate, we can see that the H gate applied on 0 becomes plus. So plus is the 1 over square 2 CAD0 plus CAD1. So this vector, and minus is 1 over square 2 CAD0 minus CAD1. So it's another vector. So one can verify that H maps 0 to plus and H maps 1 to minus. And for CNOT, one can see that it maps 0, 0 to 0, 0, but maps 1 to 1, 1, 0 to 1, 1. Because the first bits of 1, 0 is 1, so it flips the second. So this is we call a quantum circuit, or very simple quantum circuits. Is like if we input with CAD0 with 2 quantum bits, then we first apply Hadamard gate, and then we apply the CNOT gate. So one can see that the input is CAD0, 0. So when we first apply H gate on the first bit, the state becomes H applied on CAD0, tensor CAD0. It becomes plus tensor 0. And you expand it with the vector version, you can get it 1 over square 2, 1, 0, 1, 0. And then we apply C0 on that on the state after applying H gate. It becomes 1 over square 2. The first term, Cat0 apply on C0 because it's a linear operator. It does not change. But for the second one, it maps 1, 0 to 1, 1. So the vector changes, becomes 1 over square 2, 1, 0, 0, 1. So this is called maximal entangled state, or the Bail state, the famous Bail, right? You know, the Nobel Prize of this year was awarded to verify the physics, to verify the Bail inequality is the same Bail. And the tensor product is also called chronic product. It's A tensor B. It's just in this form. So if matrix A is A0 to AN0, N0N, AM0 to AMN. And then you just change every entry of A becomes a large matrix proportionally to the original entry of A. And the matrix is B, so the A tensor B. So you can see that Cat0 tensor Cat0, because Cat0 is a quantum bits, is 2-dimensional. And then you tensor them together, you can become 4-dimensional. So let me give a very rough introduction of the quantum program. So this is called quantum while program, or is simply a direct generalization of the p-while program or the classical while program. So you can see we have a skip, we have composition S0 and S1, we have initialization, Q initialized to Cat0, we have unitary operation, we have if and while. So the only difference from the first side is that the branching, the if branching or the while condition or bodyguard is quantum measurement. Means that it introduces non-deterministic or probability in the program. And we care about just the expectation of the outcome generally. So this is the operational semantics as we said. So the skip maps row to row. Row is arbitrary quantum state. Usually the notation we denote is just like P, we denote as a probability distribution. So it's a common symbol. So and unitary is just applying unitary, U row, U dagger. So you might want to ask, so why? Because you told what I said is that unitary is a linear operator, but now it's no longer, right? Because you not only apply U in front, also apply the U inverse or U dagger at the back. It's simply because now this row generally is not a vector, but a probabilistic composition or the convex combination of vectors. And mathematically, we should not regard that as a vector. Now that's a matrix. So we need to deal with we call it density matrix. So now rho is a square matrix, no longer a vector. And this initialization, we can see just the initialize the register of Q becomes 0. And if a statement is like, okay, if the measurement outcome is M0, MM, then the state becomes MM row, MM dagger. And the composition and everything else is just similar, because as long as you regard the probabilistic branching and you're summarizing everything together, then it's just notationally is direct generalization of the probabilistic while program. So there has been lots of research of quantum programming. So I just list a very little part of it. I think we can recall that back to Peter Sillinger's MSCC 04 paper. It's called Towards Quantum Programming Language. And then Ning-Shen Ying, my supervisor in 2012, provided the quantum Hall logic. So which is a complete and sound and relatively complete quantum Hall logic. And afterwards, there are lots of development include Martin Vichev's paper, and now you can see at the top conferences of programming languages, there are more and more quantum programming paper. And I just list a very, very small part of it. And there's also compiler-related work called VOQC by the Maryland group. So what do we mean by quantum program verification? So how the question we ask is similar as classical, that how do we know a quantum program is correct? It's similar as classical, it's just that we give a classical description of quantum program and the specification, and we want to see whether the program, the output satisfies this specification or not. But we don't want to execute it. So let's look back the classical world. What we do, we put in assertion, right? We print out whether this x equals to 0 as some program. Oh no, sorry, that's wrong. So, but the assertion is like the first reported by von Neumann and Goldstein in 1947, and then advocated by Turing at the paper of checking a large routine. So it's like we have a classical program logic. So classical programming logic, as far as I see, is built on the classical assertions. So the assertion is like a predicate at some program with some program variables and a certain place of the program. And then we just see whether the assertion was satisfied or not. By static analysis, of course, here. And this also can be done by dynamic analysis. So, sure, based on the assertion that Hall provided a Hall triple. Okay, so the PSQ that we all know that for classical program, S, P, and Q are assertions. So the interpretation of this Hall triple we all know is that if input satisfies this P, then the output satisfies Q. And so the formal verification is like given S, P, and Q, so we want to prove or disprove the Hall triple. And I think this is the famous example that I may do not need to say, but yes, so this computing the Euclidean, the GCD is a famous example of showing that Hall triple works by providing the loop invariant. But what kind of assertions shall we choose for quantum programs? Okay, then that leads to the second part. So our choice is like motivated by the Birkhoff and von Neumann in their famous paper called The Logic of Quantum Program of Quantum Mechanics. So in which they use projection or subspace as a property. And they say that so a subspace or in matrix version is just a square matrix, which is Hermitian and equals to square invariant. P equals to P complex conjugate, and also P equals to P squared. So it corresponds to a subspace. And because the assertion asks us to see whether the input satisfies something, so what do we mean by satisfaction? Here, a quantum state, we say rho is satisfied P if P apply on rho. This is matrix multiplication, does not change the state at all. In other words, the state or every part of the state lives in the space. So this is we call it satisfaction. And why do we use this quantum, we call it projective predicate? Because first, it's easy to implement. And second, we can easily derive an interpretation of satisfaction. And this can be used as an assertion and simplify lots of proof rules. So let's define the support. Support of A is similar as probabilistic, I would say. So suppose we have a matrix A, we decompose it into summarization of lambda I, psi I, psi I, then support A is nothing but the span of these psi I's. And the satisfaction, as we say, is that if rho satisfies P, if and only if support rho is in P, or equivalently, P rho equals to P. And we can define corresponding logical operations called negative P is defined as P perp, or the orthogonal complement of P. And we can also define P and Q and P or Q, because this is very classical. And because it's Boolean, so the projection provides the convenience of reasoning with Boolean. So in this paper called Applied Quantum Power Logic, we provided the correctness formula as PSQ. So in the sense that if the input row satisfies P, then the output S row satisfies Q. So this can be this idea can also be used for checking with measurement, because this whole triple can be checked by quantum measurement. And the good part is that quantum measurement P and I minus P will not collapse rho if rho satisfies P, in the sense that we don't need to worry about the Schrödinger's cat. Because if we verify at some certain state using some general measurement, it may collapse state, so we need to do it again. But with this projective predicates, we don't need to worry about that. So we provide a sound and complete proof system, and the proof system is simple. For skip and unitary, it's very simple. So P skip P. So if the input satisfies P, if we do not do anything, then output of course satisfies P. And for unitary operation, so if the input satisfies P dagger PU, then P dagger PU, then the output will satisfy P. So this is very simple. So for the if statement, it's like if PM, SM satisfy and Q for all M, then we can make the conclusion that all MM and PM and the output is Q. So you can see that if the input row satisfy all MM and PM, then MM apply on row and MM dagger always satisfy PM. And then in other words, each branch will satisfy Q immediately. And we can also have a loop rule. So as we said that method can be used for quantum for testing, because we introduced a assert saying that assert QP. So in the sense that if MQ is true, then we just skip. And if MQ is false, then we just abort. So this measurement, quantum measurement, is a two-outcome measurement. M true is P, and M false is 1 I minus P, or negative P. So in the sense that if the state at this stage satisfies P, then we will get true with 100%. Then we just skip. But if in any sense we get a false, then there must be something wrong. But the good thing is that as long as this assertion is passed, then P row P is P, whatever P is. Even if row at first, before this assertion does not satisfy P, but with some probability, as it passed the test, the outcome is already satisfied P. Then we go to the next program S prime, and we check whether assert QQ is satisfied. So if assert QQ is not satisfied, then must something wrong at S prime. So this will work very well for the testing purpose. And this idea has been used for the error mitigation in Cambridge quantum computing. So let me come to the third part, called quantum abstract computation. So you may have a question like, if you work with, because you start saying that Feynman and Manning saying that, okay, with 100 quantum bits, then classical computer cannot do, but static analysis, how do you do that? Even if you apply quantum Hall logic, it requires you write a giant matrix. So yes, because a quantum circuit or general current quantum algorithm mostly work as a quantum circuit is a matrix multiplication. So a general M qubit quantum state can be written as, you can see that summarization of I1 to IM, I1 tensor I2 to tensor IM. So this generally is a 2 to the M dimensional complex vector. And so for instance, that Cat0 tensor Cat0 can tensor Cat0. So all 0 state becomes a 1, 0, 0, 0, 0, 0, this giant vector. So generally, a quantum circuit is a m quantum bit, maps m quantum bit state to m quantum bit state. And in other words, a quantum program is a 2 to the m times 2 to the m dimensional matrix. But good thing is that it's with structure, because it's built by a sequence of, usually built by 1 or 2 qubit unitaries. And it usually take cat0, cat0, cat0 as input. So for simplicity, we will just say that cat0, 0, 0, 0, just ignore the tensors. So the quantum program verification, the challenge is like, first is like, what specification shall we care about? Or what property shall we use for measuring the output? And for example, this GHZ circuit, so it takes cat0, cat0, cat0 to cat0, 0, 0 plus cat1, 1, 1 divided square 2. So this Z is Zillinger, so this year's Nobel Prize winner in physics, one of them. So the specification we choose here is to prove the output is in the subspace of spanned by cat0, 0 and cat1, 1, 1. But the challenge is like there's an exponential explosion of the dimension. Because as we said that m-dimensional quantum state is the 2 to the m-dimensional vector over C. And a quantum program is generally a 2 to the m times 2 to the m matrix. And this is not a problem in classical, because classical bit strings is much simpler if we have m bits, so we just represent as B1 to Bm. So even without loop and recursion, so the consequence of this fact is that 2 to the m times 2 to the m matrix is just too large for verification, just using matrix multiplication. And as we said that, what kind of property of interest can be verified efficiently? So our general idea is just approximation plus structure. So as a static analysis, so we should just use abstract interpretation. So by Cousseau and Cousseau. So for instance, suppose one wants to compute 2.5 times 1.5. When we just go to abstract domain to see that the first entry to 2.5 is between 2 and 3, and the second 1.5 is between 1 and 2. Then just compute the abstract operator product, get that output is between 2 and 6. And this is the over approximation of the true outcome, a true result, 3.75. So if we want to use we want to use the idea of abstract interpretation to reason about quantum programs, we need to, what do we need to define? So let's see first. So the m qubit quantum state, as we say, is the 2 to the m dimensional vector space, vector over a complex vector. And the concrete set we use is a linear subspace of 2 to the m dimensional complex space. So as we use in applied quantum Hall logic. And the order we use between the concrete domain is the subspace relation. So P is in Q means that the subspace of P is in subspace of Q. And the unit part is that the concrete state always requires exponential space to represent. So how do we define the abstract state? And we need at least that the abstract state can be efficiently represented. So we use the basic idea is just dimensionality reduction. So the abstract state we define is no longer let's say the whole 100 quantum bits, but a cluster of quantum bits. So in the sense that suppose we are working with 100 quantum bits, so we just look at the first and second qubits, the second and third qubits, the third and fourth qubit, and so on. This, for instance. So in quantum mechanics, there's a terminology of calling it is called reduced density matrices. In probabilistic counterpart is just the marginal distributions. And the good thing, or the important thing is that because many important physical properties of a quantum system only depends on reduced density matrices, but not the global wave function. So as we said, we look at the cluster of quantum bits, but we not look at the reduced density matrices directly, but we just look at the projections of reduced density matrices. So this is called a local projection, and this is a quantum analog of a set. And you can regard it as the local constraints. So for instance, if you are working with a set problem, it says like the first, the second, and the third bits, there is at most there is at least one of them is not zero, or for instance. So you get local constraints of the global feasible set. So we can also define the orders between the abstract states. Says PS1 to PSK is an abstract state, and QS1 to QSK is an abstract state. So S1, each SI is just a subset of the M bits. So we say that PS1 to PSK is smaller than QS1 to QSK if for each SI, PSI is smaller than QSI. So now this is much easier to verify because PSI is nothing but a projection on qubits of SI. So SI is a subset of all, let's say, 100 bits, 100 quantum bits. So SI could be first and second bits. So in total, it's just the 2 quantum bits. The dimension is much smaller. So the specification we care about is like, okay, suppose we have a precise state. This is the quantum, the Dirac notation is satisfy PS1 to PSK if PSI apply on psi SI equals to psi SI, in the sense that the marginal distribution satisfies this PSI for each SI. So then we can define the abstract function, which maps concrete state to abstract state. So intuitively, it's like just maps global constraint to local constraint. And the concretization function is maps abstract state to concrete state. It maps local constraints to global constraint. And we can define abstract operation, U sharp for a U. U is let's say, a unitary operation or a gate applied on 1 or 2 quantum bits. U sharp should map abstract state to abstract state as the standard abstract notation says. But there's an issue. There's an issue saying that suppose we're working with U12. U12 is a gate applied on the first and second bits. But the abstract state we choose is, let's say, P01, P12. So it would be easy to see what is Q12, right? Because U12 just apply on the qubit 1 and qubit 2. So U12 sharp should just map P12 to Q12. That's not a problem. But how do we define Q01? Because if we apply U12 directly on P01, it's unclear because there's an overlap qubit, there's an untouched qubit, quantum bits. So how will this change come? In other words, the P01 does not have enough information for us to get a good approximation of Q01. So are we just directly applying the standard abstract division to quantum? Says that, suppose now we are working with the abstract state A. and which first go to concrete domain using the concretization function to gamma A, and then we apply U on this concrete state gamma A to get U gamma A U dagger. And sure, we can see that this U gamma A U dagger is a well approximation, and then we map it back to abstract state using alpha abstract function to get U sharp A. That is a way of defining U sharp. But there's an issue here. This definition is not applicable because it requires goes from the abstract domain with polynomial size go to exponential size, and then we need to work with the exponential storage, exponential size of data, and apply matrix over there and go back. So why this is an issue? Because quantumly, so we're interested in quantum because it provides computational advantage. And if we do the reasoning using exponential time and space, classically, this becomes nonsense to care about quantum computation, right? Because we caused all the computational advantage at the beginning of running the algorithm. So how can we avoid this? The idea is very simple. It's just to do partial concretization. So we go from abstract domain to a partial concrete domain. We get gamma A. And then we apply unitary over there to get U gamma A U dagger. And then map it back to get U sharp A. And between the partial concrete domain and the true concrete domain, we have some approximation relation. So in a sense that then we can show that abstract domain is the abstract function. First can be computed using infeasible time and space, but also it provides a good approximation. It provides an approximation of the concrete the true computation happens in the concrete domain. So as a running example, let me still talk about the GHZ program. So it takes cat000 as input. First, apply H gate on the first quantum bits, H gate on the second quantum bits, X gate on the third quantum bits, and then apply C0 gate between the second and third qubits, and apply C0 on the first and the last qubits, and then apply H gate on all. So as we said that we can choose the abstract state as a projection on 0, 1 qubits and 1, 2 qubits. And it's clearly that at the beginning of the computation, Q0 and Q1 is in the span of cat00. And the Q1 and Q2 also in the span of cat00. And yeah, by our knowledge, we actually know that this program will map cat00 into cat000 plus cat111 divided square 2. And we will use the notation that the plus here is 1 over square 2 cat0 plus cat1. So at the first application of H, and X, so which will maps the projection of the first 2 quantum bits cat00 into plus plus, because we said that H gate will map 0 to plus. So the first quantum H apply on the first 0, the second H on the second 0, so it maps into plus plus. And the gate H and X of the second qubit of qubits Q1 and Q2 maps cat00 into plus 1, because the H gate on qubit Q1 maps cat0 into plus, and the X gate is a NOT gate, is a NOT gate, so it's a flip gate, so it maps 0 to 1. And then we look at the first C0 gate. the first CNOT gate apply on qubit Q1, Q2. So as we said, it's very simple to say, it's direct to say that it will map the projection of the first and second qubit Q1 and Q2 into the span of K01 plus K10 divided square 2. So you just apply the matrix multiplication on plus 1. This is what we have already done in the basics of quantum computation. But the issue is that how can we update the projection or the local projection on the qubits 0 and 1? Because of the overlap, right? Because the first CNOT gate apply on qubit Q1 and Q2, but the first part of local projection is only with qubit 0 and qubit 1. So the idea is like, as we said that the local projection is a local constraint. In other words, is our knowledge of 0, 1, 2 at this stage. And this, at any stage, our knowledge of the 3 qubits is just the union of our knowledge of the first 2 qubits and our knowledge of the last 2 qubits. So we just apply CNOT on our knowledge of 0, 1, 2. Then we drop the information of 2 to get 0, 1. So this is then we can compute that, okay, after the first application of the CNOT, the state will be in the span of plus 0 and plus 1. And you can see in this example, the idea is very similar, or you can regard it as a standard abstract interpretation. Because if we combine our knowledge of 0, 1 and 1, 2, we get our knowledge of 0, 1, 2, but to represent the giant, our knowledge of 0, 1, 2 to before applying CNOT, we actually deal with the matrix with size 8 times 8. And then after applying on the second CNOT and or the H gate, one can actually verify that, okay, the output GHZ circuit is actually in the subspace of span Cat0, 0, 0 and Cat1, 1, 1, where we use that if the first 2 qubits is in the span of Cat0, 0 and Cat1, 1, and the second 2 qubits is also in the span of Cat0, 0 and Cat1, 1, then we know that overall the 3 qubits in the span of Cat0, 0 and Cat1, 1. But as we said that for combine our knowledge of 3 qubits, of our knowledge of Q0, Q1 and Q1, Q2 before applying CNOT is nothing but it's like we computed the whole concrete state because it is only 3 qubits. But we can actually do it with m quantum bits of the general GHZ program. And we still choose abstract state as in the projection on qubit 0, 1, 1, 2 to m-2, m-1. So in total, we only care about m-1 4x4 projections. And we can actually prove that this span turns out the first 2 qubits in the span of Cat0, 0, Cat1, 1, 1, and so on for each pair. So at this stage, what we can see that when we do the things on the first CNOT, we don't need to combine all the information of all our knowledge locally, but just combine the corresponding knowledge. So to reason about this, we don't. It can be done in polynomial time. So suppose we have a program with 20 qubits. So we only need to track 19 small pairs. And rather than looking at 2 to the 20, we only need to look at 19 times 16. 16 comes from the 2 quantum bits with 4 dimensions. So 4-dimension matrix at most has 16 parameters. So so we actually implement our program on on some instance, and we show that okay, we can reason for these programs up to 300 quantum bits. And if we directly write 300 quantum bits on a classical computer, then well, 2 to the 300 is too high. So there are lots of future works directions. So for instance, as we're doing static analysis, we might want to ask what can we say abstraction refinement, and can we implement it in? Can we push the quantum programming into automation, says Cork and Isabel, as the Marian group did? And how can we do the debugging? So here we only show that our idea can be used for the verification. So can we do debugging and how? And there are lots of applications. So for instance, for using the programming language idea for guiding the software and hardware design, and for instance, the architecture and OS. And I would say that there are lots of works in the architecture community of quantum already. So yeah, so these are the references that I'm using, and the most of the talk material comes from these references. And I would say the last paper is in this year's, it's in Uppsala and on Friday, and my student Peng Yan will talk about. So please come then. Yeah, I think that's all. But thank you very much.
Should I use the microphone? Oh. Thank you for the excellent talk. So you talked a lot about the difficulty of verifying and representing assertions and properties of quantum programs efficiently. Yeah. I had a question about the difficulty of writing down the specification to begin with. So in the classical case, it's usually pretty easy to write a specification that convinces you the program is correct. Yeah. So in your GCD example, right, you had write down the loop invariant. Yeah. This isn't really the case for quantum algorithms, right? So if you think about something like HHL, where you're actually trying to invert the matrix and find the eigenvalues and store them in some register, the specification that corresponds to the particular eigenvalue, that requires knowing the eigenvalue, which if you did, then you wouldn't need to run HHL or use a quantum computer in the first place, right? Which has struck me as a pretty difficult problem for using quantum specification languages overall. I was wondering if you had any thoughts on how we might overcome this difficulty.
Well, this is a very good question, and I have no idea. So I think the question is like, there are many algorithms require us to know the eigenvalue or eigenvector of a given input. I think that's generally a very difficult question, and I don't aware any approach of doing that in the programming language community, and I don't know how, because so you can see my for the specification. So if we want to reason anything, so we need to first, using static analysis, we need to represent it with very compact representation, right? For eigenvalue or for at least for eigenvector. So it's hard to say that. Well, suppose you're given like n-dimensional matrix, so how can you represent its vectors? It's eigenvector, and I think I have no idea about that, because I understand that your input matrix generally should not be a general matrix, because a general matrix will require you to like n squared representation, then the output of then eigenvalue would not be a problem at all. But since you care about a giant matrix, right? And the giant matrix, you care about the sparse giant matrix, as far as I see, right? Then how to evaluate or how to represent a giant, the eigenvalue or eigenvector of a giant sparse matrix, I have no idea. Wait. Well, do you mind to repeat your question? So am I understanding correct? Right?
No, I think you largely answered it. I mean, I was just getting at the fact that in order to write down a specification that convinces you that HHL is correct,
Yeah.
you probably need some idea of what the inverse of the matrix is and what the eigenvalues of the matrix are in the first place, right? And I think you discussed that.
Yeah, so in the sense that if you says your input matrix, right, you want to use HHL, right? So HHL is so if you don't mind, let me go to the first page. So for the others, so yeah, this AX equals to B is referred as HHL by the author's name. It solves linear systems within polynomial time, but it depends on A, right? So if your says you're caring about a square matrix A, right? So if your square matrix A is sparse, if it's general, then you require n square parameters to represent it. Then your eigenvalue or eigenvector would not be a problem because it's polynomial refer to your input, right? And so you care about sparse matrix, right? But for sparse matrix, it's still not a problem because for sparse matrix, so at least you will require each row has a non-zero elements, right? Otherwise, you can eliminate it. So then, although your input parameter will grow at least linear as a dimension, then represent your vector, your eigenvalue or eigenvalue will not be a problem at all.
I guess.
But
I don't want to take up too much time.
But there's another issue. Probably you don't. Probably you can think is that suppose A is represented as a let's say local Hamiltonian or something. Given in that sense, then you can use because you want your input as a polynomial size, but you want the eigenvector as an exponential size, right? You want to get this unbalance, but this. For if your input, let's say if your input is a local Hamiltonian formula, then then you want to bound this eigenvalue or eigenvector, that will be a too hard problem. I think it's a QMA hard or QMA complete. So then it's generally impossible, given our assumptions as some complexity assumption. I hope that answers partly answer your question. Thanks.
Yeah, thank you. I don't want to take up too much time if other people have questions.
Yeah.
So most of the algorithms we were thinking about here are parameterized by the number of qubits you're actually using in the verification. And even if you think like a simple example, let's say that's like a quantum adder, that's going to be parameterized by n, where n is the number of qubits. And it looked like the work here fixes the number of qubits. Has there been any thought on trying to generalize these to parameterized proofs where maybe you find like some structure in the circuit that you can maybe work on inductively or something to generalize the results, or maybe abstracting some of the qubits that don't matter for the properties?
Well, that's a very good question. So I think that let me repeat the question. Okay. So I think the question is sorry. Here. I think the question is like here we always assume that the system size is fixed, let's say 100 quantum bits or something. But the question is like, can you do like a parameterized reasoning? That's a very good question, and I think yeah, the core kind of Isabelle may provide some evidence that one can do that, but I don't know whether. I'm not sure. I think it's interesting to see whether our framework here can fit that. I mean, combined with the induction and the effectiveness, I think that's a good question. And we thought about it, think maybe one can go a little bit further by combining the high order logic in program analysis, in probabilistic program analysis with quantum. So but we haven't done it yet, but I think that's a good question. Thanks.
And I guess, do you mind if I add a follow-up quickly?
Yeah, sure.
So I guess one thing that kind of crossed my mind while you were talking was, if like this language wasn't talked about as much, but like in crypto, for example, there's support for defining families of circuits over like inductive data types. So I guess while I was asking the first question, it just kind of occurred to me that maybe you could actually generalize those invariants because there's already an inductive structure in the language. Do you think that makes sense?
I don't really get the question. So was the question like to find the clusters of quantum bits?
Yeah, so since the circuits are kind of inductive to begin with in some of these languages, maybe that could be exploited to simplify, like to generalize the proofs, perhaps?
I think that's a very good question, but very hard to answer because, to be honest, the way that we choose like the first and second qubit, second and third qubits, this is because we know the circuit very well. For a general circuit, we don't know how to find a good cluster of quantum bits to fit our goal of reasoning with specification. But let's look back. So it also depends on what kind of specification you're interested in, right? So suppose you care about your specification is about the output with the first and second qubit, second and third qubit. Then we may just use that and just add slightly something more to see whether it can fit, right? But generally, if you care about some correlations between n quantum bits, then I don't know.
All right, that makes sense. Thank you.
Thanks very much.
Someone else? There is a space for one more question.
I can ask, I have a couple.
Sure.
On one of the slides, I saw.
Here.
Take this.
Because of the people.
Okay, on one of the slides, I saw there was some if and only if with 0, 1, 2 qubits with the union.
Yeah.
So does that mean that there is no information lost, or
Here, right?
I think it was before.
It was before.
You just like showed it. Yeah, our knowledge of.
Yeah.
So what does this mean? Is this like precise?
We already lose information.
You lose.
We've already lose information. So you can see from here our knowledge. So at a certain stage of 3 quantum bits, so all we have is the abstract state.
Okay.
And the abstract state already is the overall approximation of the true state.
So the abstract state over 0, 1, 2.
Yeah.
And then if you decompose it into 2 parts, you don't lose any information with respect to the abstract states.
Very good question. We might lose during that process, but generally we will not. It's possible to lose something.
And a more futuristic question. Currently, you are verifying quantum programs on classical computers.
Yeah.
If you could actually verify on quantum computers, I think it's a bit far away. How would this abstraction, any idea, how would this change?
Oh, this is a very good question. So let me go back here. So I think, let's see here. Yeah. So I would say that the techniques and ideas of stack analysis can always be used for testing. And for instance, this is just the use of applied quantum Hall logic idea to use projection as assertion. But I've been thinking about using the abstract interpretation idea to use the dynamic times, but it's not so smooth. It's very, very interesting question because for generally speaking, so for abstract interpretation, quantum abstract interpretation, we care about is just the relation between global and local. And then certain entanglement will come, and we know that entanglement is hard to do. So, but that's very nice suggestion. Thanks.
Okay, thank you.
Thanks.
So let's thank the speaker again for his wonderful talk.
Thanks very much.